Hello everybody. All right, I am doing a cool video on how to do these problems. All right, this is an absolute ratio test if you want to, but because this guy right here is centered at 3, we know the answer has to be centered at 3. Negative 2 to 8, negative 2 to 8, negative 2 to 8 is centered at 3. Negative 5 to 5 is not. Neither of these are centered at 3, they're centered at 0. So what I'm going to do is I'm just going to focus on these 3 and cheat a little bit by only plugging in the endpoints. So if you plug in your negative 2 into the x, you get negative 2 minus 3 to the nth over n squared 5 to the n. But that is negative, so this is x equals negative 2 we're plugging in. But then you get negative 5 to the n over n squared 5 to the n. But that is, I'm going to hit kitchen table. Negative 5 to the n is negative 1 to the n 5 to the n. But look at this, your 5 to the n's cancel out, and you're left with negative 1 to the n over n squared. This is an alternating series test. Converger, because it sign flips, and because 1 over n squared goes to 0, this guy is a converger by the alternating series test. That means negative 2 works. So this guy is good, or this guy is good. B is now out. Now comes the clincher. We're going to go to x equals 8. When you go to x equals 8, we're going to have 8 minus 3 is 5 to the n over n squared 5 to the n. But of course, our 5 to the n's cancel. We got 1 over n squared, but this is a p series. 2 is bigger than 1 converger, so this guy converges as well. So I'm going to include both ends, and that's why my answer is A. All right, here comes number 2. Number 2, and if you want to know how to do absolute ratio test again, let me know, and we can help you with that. Number 2. Now, what's nice about these, I'm going to do this. What's nice about these is that this is a tricky one. This is a tricky problem. So there's several ways to do this. What you could do is you could actually write out the first few terms of this series. So we're like, if I stick in a 0, I just get 2x to the first over 0 bang, 1, plus if I stick in a 1, 2x plus 1 squared over 1, 2, 2x plus 1 cubed over 2 bang, 2x plus 1 to the 4th over 3 bang, etc., etc. But then f prime, so I'm going to take the derivative of this twice and then just stick in negative a half. So if I take my first derivative is just 2 plus, now watch this, 2x plus 1 to the first times 2. This guy, 3, 2x plus 1 squared times 2 over 2 bang. This guy, 4, 2x plus 1 cubed times 2 over 3 bang. But notice what happens here. On my second derivative, this one's gone. I could have already known that. This one, now right now, this is actually, what is it? 8x plus 4. So my derivative of this part is 8. My derivative of this part is like a 6 times a 2x plus 1 times 2 times the other 2 over 2 bang from the chain rule. But this one still has a 2x plus 1. And this one still has a 2x plus 1. And so on and so on. All of the rest of these have a 2x plus 1. Every one of these is gone. That's the only thing we're left with. And it's got to be E8. But you could have snuck this in a little bit and focusing on only this term. Because boom, boom, boom. Excuse me. Or you could have looked at this and said, oh, wait a minute. I'm just going to take my second derivative. This is tricky. Take my second derivative of the nth term times 2 over n bang. That's my first derivative. My second derivative would be n times n plus 1 times 2x plus 1 to the n minus 1 times 2 all over n bang. And then you could write out a couple terms of this series, excuse me, and then stick in negative a half. But this would be the series that generate it, and would give you the 0 and the 8, and it's just going to end up being 8. So that's kind of a nice thing to do. Okay. Number 3 is kind of a cute little problem. And if you want any more explanation of any of these, of course, just ask. This one is kind of nice. So this is kind of like the quick version of each of these. If y to the n means nth derivative, the smallest positive number for which the nth derivative is y again has to be, if it's sine, 4. And you know this because sine, watch this, the first derivative is cosine, the second derivative is negative sine, the third derivative is negative cosine, and the fourth derivative is back to sine. The smallest positive integer for what the fourth is just the same as it again has got to be 4. And there's our first three, A, E, B. Now we go. We're just going to do the multiple choice for this video. And I'll save the FRQ for another one because we'll see if this is even watchable. All right. For which the series is e to the negative 2x squared. Now we know e to the something is 1 plus something squared. How's it going memorizing these, huh? You guys are getting pretty good at memorizing your 7 Maclaurin series plus the blah, blah, blah. So if I do that, I'm certainly not going to be right now using the Maclaurin series formula to generate this whole thing. I'm just going to go, oh, this is going to be 1 plus the negative 2x squared goes into here. Negative 2x squared plus. Now already we should have a 1 minus 2x squared. And this is the only one. That's the only one. Because we're replacing. Let's make sure. One more. Negative 2x squared. Negative 2x squared. Squared over 2 bang. But this term is just 4x to the 4th over 2 bang. And what do you know? Make sure there's none other one like that. There's that one, but it should sign flip because we're putting in a negative. That's not the right one. That's the other one. It's got to be B. Okay, that was kind of cute. Okay, here's this. Now this one's kind of tricky. I said way over here, hint Lie8. And what that means is ultraviolet voodoo, integration by parts. The integral of u dv equals uv minus integral v du. I need a u and something that's being multiplied by it. But the problem is there's only one thing. Luckily, inverse trig is like the second thing on my list. Logs. Are there logs? No. Is there inverse trig? Yes. Is there algebra, trig, exponential? Inverse trig. So I'm going to pick u as my inverse trig function. So my dv is everything left over, and that's just dx. So that means v is x, and my derivative of u is, remember this, 1 over the square root of 1 minus x squared. That's the derivative of sine inverse, the inverse trig derivative. You should memorize that. So now, if I go uv, u times v minus integral v times du. When you multiply these two together, the x is going to go on top. We're still going from 0 to 1. We're not subbing anything. It's still 0 to 1. But this is a u sub. Interesting. It's like a built-in u sub into an ultraviolet voodoo. So now I'm going to pause and say, well, this is a u sub. U is 1 minus x squared. So du is negative 2x dx. And I've actually got that. I'm not going to mess with the negative yet because there is a negative there. But x dx is negative 1/2 of du. So this becomes, okay, I got to think here. X sine inverse of x minus the quantity of, now here we go, negative 1/2 integral of 1 over u, because the negative 1/2 became the x dx, 1 over root u rather, 1 over root u. And luckily, this becomes x sine, it's almost like it's by design, plus 1 over 2 root u's integral. How cute is that? I just put the 2 back in. We know the integral of 1 over 2 root u is root u. So it's x sine inverse x plus root u. But what was u? What was u? Where was u at? U was, where am I? Here. Finally, I can go from 0 to 1 because everything's back into x's. So I'm going to go 1 times sine inverse of 1. Now you remember, sine inverse means where is sine 1? Where is sine 1? From negative pi over 2 to pi over 2, and that's at pi over 2. So 1 times sine of inverse of 1, which is pi over 2, plus square root of 1 minus 1, which is 0, minus, now don't discount the 0, even though 0 into this one is 0, but plus the square root of 1 minus 0 is the square root of 1. So we have pi over 2 minus 1, which is not one of our options. So I think we need a common denominator, pi over 2 minus 2 over 2, which is pi minus 2 over 2. Hey-oh, C. Hope that's right. Number 6. This one is kind of sneaky. You can do this 3 different ways. 3 different ways. Watch this. The easiest way is to say, well, let me not do the easiest way first. You know how, parametrically speaking, dy dx is dy dt over dx dt. We know that. Now, dy dt is the derivative of y, which is just f prime. F prime. But dx dt is a chain rule. 2 times f times the derivative of the something. But looky, looky, the f primes cancel out. You're just left with 1 over 2f. But to take the second derivative parametrically, the formula is, we have to do the first derivative with respect to t of dy dx, and then divide it by dx dt, so we're sneakishly ddxing it. Doop, beep, boop, beep, boop, boop, beep. And then we've got the derivative with respect to t of dy dx, which is 1 over 2f of t, over dx dt, which was already 2f f prime. Now, this is 1 over something. Maybe we could do quotient rule, maybe that might be simplest, but this could be 1 over something, negative 1 over something squared times derivative of something, or bottom times derivative of top, which is 0, minus, here we go, top times the derivative of the bottom. But the derivative of 2f is 2f prime all over the bottom squared. If you square 2f's, it's 4f squared. But that's all over 2f f prime. Now, careful. If you multiply by the reciprocal, these two portions go together, n'est-ce pas? So I'm going to have negative 2f prime all over 8 f cubed f prime. Luckily, the f primes cancel out. 2/8 is 1/4, and I get negative 1/4 f of t cubed, whoop, whoop, e. But, check this out. What you could have done at the very beginning is said, un momento, x is equal to y squared, because isn't y that? And if x is equal to y squared, that means y is equal to plus or minus root x. Let's take the positive one. If y is root x, y prime is 1 over 2 root x. First derivative, second derivative. That means y double prime is bottom time, or you could just call this 1/2 x to the negative 1/2. There you go, because it's equivalent. It's equivalent because it's the power. So y double prime is negative 1/4 x to the negative 3/2. But that's aka 1 over 4, 1 over x to the 3/2. But x to the 1/2 was y. So this is negative 1 over 4 y cubed. What? Slick. Okay. And last but not least, 7, 8, 9. Uh-oh, I need my calculator. That doesn't have a pause on it, so I'm just going to go grab my calculator. I hope that's it. There it is. Oh, I hope I get this right. The base of a solid region for this quadrant. Now, this is interesting. I don't really know what this looks like. Oh, I've been in polar mode. How fun. Function mode, y equals, memories again, eh? Okay. So I'm going to go here, and I'm going to go, what is the heck is this? 3 to the, where's that button? That's what I get for switching calculators. Negative x squared minus 1/3. Get. First quadrant bound by the axis of this. Okay, so we're like, all right, what in the world is this? So if I zoom 6 this, it's going to be, something's going to be going on up over here. And it's like, oh my gosh, what is that? So I'm gonna zoom in, obviously. Now that looks like 0 to 1. So I'm just going to go like, make my window like, oh, that's nice. It's nicer than a dot cam. I'm gonna make my window like -1. Maybe I could just hook up an iPhone to be my document camera to like 3, and -1 to like 3. And let's just see what that gives us. And we've got this cute little region here that's here to here. And I wonder if it crosses at 1. It kind of looks like it, so I'm going to cheat a little bit and trace to 1 and see. Is it thinking? No. Trace. Hey, 1, 0. You're like, I knew that, because 3 to the -1 is 1/3, and they cross at 0. Okay, so I've got this cute little region here, and my y-intercept is when x is equal to 0. So it's not really going to matter, because each cross-section perpendicular to the x-axis of this weird-looking that ends at 1, which is all I need, is a rectangle with a base in the xy plane, a height that is 2 more. This is the base. Now, if we sort of flip this, you're like, oh yeah, it's these. The base, the height of the rectangle, each of these cute little rectangles has a base that is the function. The function itself is the base. The height is 2 more, not 2 times, 2 more. So what we're gonna do, sorry about the light there. Sorry about the light, it's kind of cool. What we're gonna do is call that 3 to the -x squared minus 1/3 plus 2, but that -1/3 plus 2 is 5/3, because 2 minus 1/3 is 1 2/3. So that's the height. So guess what? I am going to go collecting. Let's collect along the x-axis the area of this rectangle. And the area of this rectangle has to be, oh, I got to squeeze it in here. The base times the height. Sorry, I got to shove that whole thing in from 0 to 1 and hope for the best. Now, the interesting thing is, look at this. Since I've got that in my y1, I can cheat, and I go math 9. I'm going to go, let's integrate from 0 to 1. Watch this trickery. Oops, wrong way. y1 times quantity. You see it coming. Here it comes. y1 plus 2. Sneaky. Base times height. Don't even need to worry about it. And I do this, and I get 0.992248, and I hope that's right. 0.992. Hey-oh! And I got 2 more. My family's coming in, but I'm going to keep talking. Okay, number 8. And I'm almost done. Number 8. This is really clean. This is a first derivative of a parametric. So I'm going to go dy dx is dy dt over dx dt. And dy dt is the derivative of that, which is 2e to the t. Dx dt is just clean old 2t. The t's cancel, and I'm left with e to the t over t. I'm going to have survey. There, survey says letter A. Hey-o! So we got D, then A. And our last one, this one's kind of fun. Good old, what's this called? Optimization. The value of A that maximizes the, okay. A rectangle is to be inscribed between the parabola y equals 4 minus x squared, which is an upside down parabola, and the x-axis. So you're sticking a rectangle inside underneath this. You know that there is some random x value from 0 to 2, which is the 0 of 4 minus x squared. But I already know that the height of this rectangle is going to be the function itself, 4 minus x squared. So guess what? The area of this rectangle that I'm trying to maximize is base, which happens to be 2x's, times height, which is 4 minus x squared. Now, if my area, I'm going to simplify this because I'd rather not product rule. I'd rather just use the power rule. My area is 8x minus 2x cubed. So that means okay, so this is an upside down cubic. Upside down cubic. I'm looking for that. I'm trying to find the place that maximizes the area. And maximizing the area is the place on its domain, 0 to 2, where x achieves a maximum. So I'm going to take the derivative of this and get 8 minus 6x squared. Set that equal to 0. Ask it, when are you equal to 0? Because when a function is equal to 0, it could be a min, a max, or a saddle up, or a saddle down. Saddle down, everybody. Okay, so I'm hoping for this guy right here. Boop, boop, boop. Okay, so when I go, oh geez, let's set this equal to 0. X squared equals, what is that, 8/6? 8/6, 4/3. So x equals the square root of that, which is 2 over root 3. And it's the only one. It's the only one that I got. And actually, it's plus or minus, which makes sense. Because if you actually did an A prime from 0, okay, Hazel. From 0 to 2, the only one we have is 2 divided by 1 and a bit, which is less than 2. So we're going to have this 2 over, that's a wall, 2 over root 3, Hazel. And that's going to go, I'm going to cheat here. It's going to go, oh, hold on. Oh, the whole entire thing. Ryan, can you get that? It's up and down. That's a maximum. If you don't like that, you can go a double prime is negative 12x. And if you stick in a 2 over root 3, this is party central. Negative 12 times 2 over root 3. And we get negative 24 over root 3. But who cares? Because it's negative, which means if my first derivative is 0, and my second derivative is negative, it is a maximum. So we did it. We found it. And it's right here. And page 3 goes DAB. Thank you.